Hello and welcome back. Right now, we're going to go over the last thing you need to learn before building your own neural network, and that is the activation function, which forms the layers. So recall what we've gone through so far. You've learned how to build a linear classifier, learned how to score the outputs of that classifier, and you've learned how to update the parameters W in order to minimize the loss of that classifier, and that is the whole fundamental basis of machine learning. Now we are going to go over the magic part of deep learning, and that is in how to induce nonlinearity into your classifier and turn it into a neural network. So activation functions in different contexts are also called neurons. And what they do is they will take your input and give you an output of either 0 or some value, basically in order to create this non-linearity and allow your classifier to take on a whole wide range of non-linear values so that you have to spend less time on feature engineering and so on. So here are 4 common activation functions. I'm going to go through the sigmoid in more depth, and I'm going to explain how the choice of activation functions influences the outcome and trainability of your models. There are some that are always better than others. And there are more activation functions being created all the time. It's also a significant area of research. If you are doing ML research, one thing you might want to do is to design a new activation function. So let's look at the classic sigmoid function. It's not commonly used, but it's definitely the most classic activation function. This is what you'll see quite often when people talk about neurons. What this activation function does is it takes some input x and returns a value 1 over 1 plus e to the negative x. What this does is it squashes any numbers fed into it into this range between 0 and 1. So one thing to be aware of with neural networks is that you can saturate neurons, and that kills the gradients during backpropagation, which we definitely do not want. So let's think about how signal might vanish if you pass it on through too many layers of neural networks. Recall from the backpropagation exercise that you will pass some input through a sigmoid gate, and you will be calculating the local gradients backwards in the other direction. And you can have an analytic value for the derivative of sigmoid over dx. And that has the value of sigmoid x times 1 minus sigmoid x. Let's work through the numbers here. What happens when x equals 10? You get a value very close to 0. What happens when x equals 0? You get a value 0.25. When x equals negative 10, you get a value that is very close to 0. So here, this graph kind of simplifies for you the possible values that the derivative of sigmoid with respect to the derivative of d sigmoid over dx can take. And it's really between 0 and 0.25. And if you keep multiplying sigmoid layers by each other, it pass signals through multiple sigmoid layers, what happens is that any number that you multiply by a fraction of 1 gets smaller and smaller. So think about how we multiply local gradients with a signal passed backwards from the last neuron, like this in this direction. You may have a gradient value that's high here, but gets squashed and smaller and smaller and smaller until it's dead. Why is this such a bad thing? Recall our weights updating function. If your gradient is dead, then your weights will no longer update. If the gradient at each step is too small, the training could converge even without achieving global minima for the loss function. Small gradients means a stop in training. This small gradient problem is called the vanishing gradient problem. And it's one that there are a number of ways to address it, and one is in your choice of activation function, perhaps. For people working with language, LSTM tackles this problem nicely for recurrent neural networks. So if you're running into problems with a recurrent neural network that's taking forever to train, you might want to just switch formats to LSTM. So something to think about for a minute. Is a gradient more likely to vanish closer to the input layer or closer to the output layer? it is more likely to vanish closer to the input layer. Think about how this may happen. If you are multiplying gradients from the output layer backwards, then it's more likely to vanish closer to the input. This means that if you are able to look at the gradient of each layer in the neural network, and you really can just focus on the first half even, and if your gradients are vanishing, then you know that this is the source of the issue. The sigmoid function also has another issue where the outputs are not zero-centered. I'm not going to go into too much detail onto why that's a disadvantage, only that it definitely is. If you want to think through that, look through the CS231 slides and work it out. And the other problem with the sigmoid function is that calculating e to the x is computationally expensive. Think about how you would compute e as a floating point to the x. It's kind of messy. So you have another activation here, tanh, which is strictly better than sigmoid. It has all the good parts of sigmoid while being better. It's zero-centered, but it still kills the gradients. But it doesn't kill the gradients quite as quickly because it can take values from 0 to 1. Always pick tanh if you are using a sigmoid activation function. One way you can immediately improve performance is to swap it out. Now let's talk about ReLUs. ReLUs are very interesting because they do not saturate in the positive region. They're computationally efficient. It's much easier to calculate the maximum value of 0 and x than it is to calculate 1 over 1 plus e to the x across millions and millions of operations. And in practice, it converges faster than sigmoid and tanh. So for any value you feed into it, it'll either give you 0 or positive values x. It can still die. Look at here. It can still die if the gradients you keep feeding it have negative values. It'll just like snap off and then dead. But for the most part, it is better than sigmoid and tanh. Any gradient that is non-zero gets maintained through. Anything that's less than 0, this one can still die, but this one might be positive, so still better. Now, a leaky ReLU is strictly better than ReLU. Think about ReLU's dying neuron problem there. You can solve that. Someone figured this out by just, instead of using 0, just using 0.1x, which is an arbitrary value. You can set this to any value. What you don't want to do is set this to 1, because then obviously it stops being a nonlinear function and becomes another linear operation. So in practice, use ReLU. Try leaky ReLU to see if that will help you out. Don't use sigmoid anymore. Older textbooks still use sigmoid as the primary example, but in recent years, it's really not as effective as the ReLU methods. All right, now let's move on to coding our first two-layer neural network.